Good evening. Positioned above the planet's surface, an envelope of air that's wide and layered carries out surrounding of the Earth, carrying out movement slowly and steadily as part of systems that are natural and larger. The atmosphere doesn't stay in a state that's still, yet its changes carry out unfolding without urgency being present. Layers carry out rising, one positioned above another. Temperatures carry out shifting gradually with height, and air carries out circulation in patterns that have carried out continuing for periods that are long. A layer of gases known as the atmosphere surrounds Earth. From the planet's surface outward into space, this layer creates a continuous envelope, becoming gradually less dense as height increases. What it consists of is a mixture of gases, particles held in suspension, and water vapor in varying amounts, all kept in place through gravitational attraction. No sharply defined upper boundary exists for the atmosphere. Instead, it undergoes progressive thinning, with particles becoming more widely spaced as distance from the surface grows. Its presence makes possible the conditions under which air pressure, wind, clouds, and many other natural processes can exist. The atmosphere also functions as the medium that allows energy from the sun to travel toward the surface and through which heat from the surface moves upward again. Within this gaseous layer, physical and chemical interactions take place, creating continuous links with the oceans, land surfaces, and regions covered by ice. The atmosphere's structure doesn't show uniformity, and its properties undergo changes with altitude, temperature, and composition. These variations give scientists the ability to distinguish different layers, with each one having its own temperature pattern and physical behavior. Despite extending to great vertical distances, the atmosphere stays as a thin covering when compared with the planet's size itself. Yet it assumes a central role in shaping environmental conditions across the globe. Gravity holds the atmosphere close to Earth. Gas molecules get drawn toward the planet's center through gravitational attraction, which prevents them from dispersing freely into space. Each molecule of nitrogen, oxygen, and other gases possesses mass, and this mass responds to the gravitational pull in the same manner as solid or liquid matter. The highest concentration of atmospheric gases is found nearest the surface as a result, where the pull shows its strongest effect, and where collisions between molecules happen most frequently. At altitudes that are higher, the pull of gravity continues to be present, but the number of molecules undergoes decrease, leading to a reduction in density that's gradual. This balance between the outward motion of gas particles moving fast and the inward pull of gravity establishes the atmosphere as a system that's stable but dynamic. Some particles that are very light, particularly in the outermost regions, can reach speeds that give them the ability to escape. But this happens slowly and doesn't disrupt the overall structure. The continual presence of gravity also brings about air pressure, as the weight of air that lies above presses downward. This pressure has influence over how air moves and how gases get distributed vertically. Without gravitational attraction, gases would undergo spreading outward, and the organized layering of the atmosphere wouldn't be maintained. The atmosphere undergoes thinning with increasing altitude. This thinning gets expressed as a decrease that's steady in both air density and pressure as height above the surface increases. Near the ground, gas molecules exist relatively close together, which leads to frequent collisions and pressure that's higher. As altitude undergoes rising, the number of molecules within a given volume of space shows decline, and the average distance between them undergoes increase. This reduction takes place smoothly rather than in steps that are sudden, creating a gradient that's continuous from air that's denser lower down to regions that are very sparse higher up. The thinning of the atmosphere has effects on many physical processes, including the transfer of heat, the formation of clouds, and the behavior of sound and radiation. It also has influence on how aircraft carry out their operations and how instruments receive design to measure atmospheric properties. Temperature patterns, chemical reactions, and the distribution of water vapor all show response to changes in density with height. The gradual nature of this thinning gives scientists the ability to model the atmosphere using principles of gas behavior, gravity, and energy balance. Even though the atmosphere extends far above the surface, the majority of its mass stays concentrated in the portion that's lower, with the layers that are upper containing only a fraction that's small of the total. Most of the atmosphere's mass exists within the lowest 10 kilometers. This region that's lower, close to the surface, contains the bulk of air molecules and therefore most of the atmosphere's weight. Because gravity exerts pulling on gases downward, the concentration of nitrogen, oxygen, and other components shows its greatest level in this zone. Air pressure undergoes rapid decrease with height here, reflecting how much of the atmosphere's mass has already positioned itself below. Weather processes such as cloud formation, wind systems, and precipitation take place largely within this portion that's lower, where water vapor shows most abundance and vertical motion is common. The presence of mountains, oceans, vegetation, and land surfaces that vary also has influence on conditions in this region, as heat and moisture undergo exchange between the surface and the air positioned above. The concentration of mass near the surface means that changes in temperature or pressure at these levels can produce effects that are widespread on air movement. Instruments that receive designed to measure atmospheric properties often direct their focus on this zone that's lower because of its importance for circulation and energy transfer. Although the atmosphere keeps going far above, the layers that are upper contain amounts of mass that are progressively smaller, making the part that's lowest central to many atmospheric behaviors that get observed. The atmosphere receives division into layers that are distinct based on temperature patterns. Scientists carry out classification of these layers by observing how temperature undergoes change with altitude, since these patterns provide revelation of differences in energy absorption and physical processes. Each layer gets defined by a trend that's characteristic, such as temperature decreasing or increasing with height, and by the boundaries where these trends undergo shifts. These divisions provide help in organizing the study of atmospheric behavior, allowing understanding that's clearer of how radiation, chemistry, and motion show variation vertically. The layers don't receive separation by barriers that are solid, but by transitions that are gradual, where temperature patterns undergo reversal or change slope. Within each layer, the interaction of solar radiation, gas composition, and pressure brings about conditions that are unique. Some layers carry out absorption of specific types of radiation, while others receive marking by mixing that's strong and vertical, or by air that's very thin. The classification into layers also provides assistance in interpreting satellite measurements and in carrying out modeling of global circulation. By examining temperature structure, scientists can carry out distinguishing of regions that show different behaviors despite all being part of the same envelope that's gaseous and continuous. This arrangement that's layered provides a framework for describing the atmosphere's structure in a way that's consistent and measurable. These layers include the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each of these regions receives identification by a pattern that's distinct in how temperature undergoes change with height, which provides reflection of differences in energy, absorption, and the behavior of gases. The troposphere creates the layer that's lowest, followed in order by the stratosphere, mesosphere, thermosphere, and finally the exosphere at the edge that's outer. The boundaries between them receive the name of pauses, where temperature trends undergo shift in direction. These divisions provide a way that's structured to describe a system that would otherwise show appearance as continuous and gradually changing. Although the layers receive description separately, air and energy still carry out movement between them through circulation, radiation, and wave motion. chemical composition can also show variation from one layer to another, especially at heights that are greater, where gases that are lighter become more common. Pressure and density undergo steady decline through all layers, but temperature patterns provide the main basis for classification. This structure that's layered allows observations from balloons, aircraft, and satellites to receive comparison within a framework that's common. It also provides help in explaining why certain phenomena, such as cloud formation or ionization, receive concentration in altitude ranges that are specific. The troposphere is the layer that's atmospheric and lowest. It has its beginning at the surface and extends upward to a height that's average of about 8 kilometers near the poles and about 16 kilometers near the equator. This variation in height receives linking to differences in temperature and circulation across latitudes. The troposphere contains most of the atmosphere's mass and nearly all of its water vapor. Air in this layer exists in motion that's constant due to heating at the surface, which creates currents that rise and sink. These motions that are vertical contribute to mixing, making the troposphere relatively uniform in composition when compared with layers that are higher. Temperature generally undergoes decrease with height here because the surface is the main source of heat, and air undergoes cooling as it rises and expands. Pressure also shows decline that's steady with altitude, affecting how gases carry out their behavior and how moisture undergoes condensation. The boundary that's upper of the troposphere carries out action as a limit to most activity that's vertical and weather-related, though some exchange with the layer positioned above does take place because of its density and activity. This layer assumes a role that's central in the distribution of heat and moisture around the planet. Most weather processes take place within the troposphere. This includes the formation of clouds, the development of systems that are wind-related, and the movement of masses of air. Water vapor receives concentration in this layer, making it the region that's main where condensation and precipitation can occur. Heating of the surface by radiation that's solar causes air near the ground to undergo warming, expansion, and rising, setting up patterns of circulation. As air undergoes rising, it cools, which can lead to the formation of droplets or crystals of ice that make up clouds. Differences that are horizontal in temperature and pressure carry out driving of wind, while Earth's rotation has influence on its direction. Turbulence, convection, and circulation, that's large scale, all carry out interaction within this layer, producing a range that's wide of atmospheric motions. Because the troposphere contains most of the mass that's atmospheric, it also holds the share that's greatest of energy involved in systems that are weather-related. The exchange of heat and moisture between the surface and the air positioned above shows most activity here. These processes that are ongoing make the troposphere the part that's most dynamically changing of the atmosphere. Air temperature generally undergoes decrease with height in the troposphere. This pattern takes place because the surface carries out absorption of solar radiation and then carries out transfer of heat to the air positioned above it. As air undergoes rising, it moves into regions of pressure that's lower, allowing it to undergo expansion. Expansion has requirement of energy, which leads to cooling. This process brings about a decrease in temperature that's average of about 6.5 degrees Celsius per kilometre, though the rate that's exact can show variation depending on moisture and conditions that are local. The decrease in temperature with height has influence on cloud formation, as air that's cooling can reach saturation and allow condensation to take place. It also has effect on stability, since the rate of cooling carries out determination of whether air that's rising continues upward or returns downward. In regions where temperature undergoes decrease, that's rapid with height, motion that's vertical receives encouragement, while decreases that are slower promote stability. The pattern of temperature in this layer creates contrast with that of the stratosphere positioned above, where temperature undergoes increase with height. This difference creates a boundary that provides help in limiting mixing that's vertical between layers. The boundary positioned above the troposphere receives the name tropopause. This region carries out marking of the transition between the troposphere and the stratosphere and receives definition by a change in the trend of temperature. At the tropopause, the decrease of temperature with height undergoes slowing or stopping, and above it, temperatures start to undergo increase. The height of the tropopause shows variation with latitude and season, generally being higher in regions that are warmer and lower in ones that are colder. It carries out action as a barrier to most movement of air that's vertical from the troposphere, providing help in confining systems that are weather-related below. The stability that's relative of this boundary has influence on the structure that's vertical of circulation that's atmospheric. Aircraft that carry out travel over distances that are long often carry out flying near this level, to avoid much of the turbulence found at positions that are lower down. Exchange of air across the tropopause does take place, but receives limitation when compared with mixing within the troposphere. The tropopause, therefore, assumes a role that's important in separating the atmosphere that's lower and more turbulent from the layer that's more stable and positioned above. The stratosphere exists positioned above the troposphere. This layer extends from the tropopause to an altitude of roughly 50 kilometers, though its height that's exact can show variation. air density here is lower than in the troposphere, and mixing that's vertical receives more limitation. The stratosphere receives characterization by an increase that's gradual in temperature with height, which shows difference from the pattern positioned below. This structure of temperature contributes to stability that's greater, reducing the strength of currents of air that are vertical. Winds in this region tend to carry out movement that's more smooth in directions that are horizontal over distances that are long. Water vapor shows much less abundance here than in the troposphere, and formation of clouds is less common. Processes that are chemical in the stratosphere assume a role that's important in carrying out absorption of certain types of radiation that's solar. The conditions that are clearer and more stable of this layer make it distinct in both motion and composition when compared with the region positioned beneath it. Temperature undergoes increase with height in the stratosphere. This pattern takes place mainly because molecules of ozone carry out absorption of radiation that's ultraviolet from the sun and carry out conversion of it into heat. As a result, the stratosphere that's upper is warmer than the part that's lower. The increase in temperature creates a structure that's stable and that shows resistance to mixing that's vertical of air. In such conditions, parcels of air that receive displacement upward or downward tend to undergo return toward their levels that are original. This stability allows layers that are thin of gases and particles to stay separated for periods that are long. The profile of temperature also has influence on patterns of wind, including currents that are high altitude and strong that carry out circling of the globe. Changes that are seasonal in sunlight can cause shifts in temperature and circulation that are stratospheric. The warming with height carries out distinguishing of this layer clearly from the mesosphere that's cooler and positioned above, and the troposphere that's cooler and positioned below. The layer of ozone receives location within the stratosphere. This region contains concentrations that are higher of ozone than other parts of the atmosphere, though ozone stays as a gas that's trace overall. Ozone consists of 3 atoms of oxygen that receive bonding together, forming a molecule that carries out interaction strongly with radiation that's ultraviolet. The concentration of ozone shows variation with altitude, latitude, and season. Most ozone receives finding between about 15 and 35 kilometers above the surface. The presence of this layer has effect on the distribution of temperature within the stratosphere by carrying out absorption of energy. Reactions that are chemical and involving ozone also create connection with other gases that are trace in the region. The layer of ozone is not a layer that's separate and physical, but a zone of concentration that's enhanced within the stratosphere that's broader. Ozone carries out absorption of a portion of radiation that's ultraviolet from the sun. When photons that are ultraviolet carry out interaction with molecules of ozone, energy receives transfer and undergoes conversion into heat. This absorption carries out reduction of the amount of radiation that's high energy, that reaches levels that are lower of the atmosphere. The process contributes to the increase in temperature with height that receives observation in the stratosphere. It also has influence on reactions that are chemical by carrying out breaking apart of some molecules and allowing others to undergo formation. The balance between creation of ozone and destruction maintains its concentration that's overall. Variations in radiation that's solar and circulation that's atmospheric can lead to changes in how ozone receives distribution. Through these interactions, ozone assumes a role that's central in the balance of energy and structure, that's chemical of the atmosphere that's upper. The mesosphere exists positioned above the stratosphere. It extends from the stratopause to about 85 kilometers in altitude. In this layer, temperature again undergoes decrease with height, reaching some of the values that are lowest found in the atmosphere. Air density becomes very low, and molecules of gas receive spacing far apart when compared with conditions at the surface. The mesosphere is a region where meteoroids that are small often carry out burning up due to collisions with particles that are atmospheric. Motions that are vertical, including waves that carry out travel upward from layers that are lower, have influence on temperature and circulation here. Water vapor shows presence in amounts that are very small, and formation of clouds is rare, though clouds that are high altitude and special can take place. The mesosphere carries out marking of a transition toward the conditions that are much thinner and more energetic of the thermosphere positioned above. Temperatures undergo decrease with height in the mesosphere. This cooling takes place because there are few molecules available to carry out absorption of radiation that's solar, and heat from positions below becomes less influential with altitude that's increasing. As air density undergoes dropping, the ability of gases to carry out retention of heat also shows decline. The part that's upper of this layer reaches some of the temperatures that are lowest in the atmosphere. These conditions of temperature have effect on the behavior of waves and motions that carry out travel upward from layers that are lower. The pattern of temperature that's decreasing carries out distinguishing of the mesosphere from the stratosphere that's warmer and positioned below, and the thermosphere that's warmer and positioned above. Processes that are radiative rather than heating that's direct from the surface assume a role that's stronger in carrying out control of energy here. Because of the air that's thin, changes that are small in energy input can bring about variations in temperature that are noticeable. This structure of temperature carries out defining of the mesosphere as a region that's distinct in the profile, that's vertical of the atmosphere. The mesopause carries out marking of the boundary that's upper of the mesosphere. It receives definition as the level where the decrease in temperature with height reaches a minimum before starting to undergo rise again in the thermosphere. This boundary typically takes place near an altitude of about 85 kilometers, though it can show variation with location and season. The mesopause provides representation of one of the regions that are coldest in the atmosphere. It carries out action as a zone of transition between two layers, with trends of temperature that are opposite. Waves and tides carrying out movement upward from levels that are lower can have influence on its height and temperature. Because air density is extremely low at this altitude, processes that are physical show difference greatly from those near the surface. The mesopause provides service as a point of reference that's important in studies that are atmospheric and observations that are satellite-based. The thermosphere exists positioned above the mesosphere. It extends from the mesopause upward for several hundred kilometers. In this region, temperature undergoes increase with height due to the absorption of radiation that's solar and high energy by molecules of gas that are sparse. Although temperatures are high in terms of energy that's molecular, the air is so thin that content of heat that's total stays low. Composition of gas starts to undergo change here, with elements that are lighter becoming more common at heights that are greater. Collisions between particles take place with frequency that's less than in layers that are lower. The thermosphere contains regions of gases that are ionized and that carry out interaction with activity that's solar. This layer also carries out overlapping with the paths of many satellites and spacecraft in orbit that's low around Earth. Its structure and behavior receive influence from variations in radiation that's solar over time. Temperatures undergo rise that's sharp with height in the thermosphere. This warming receives result from the absorption of radiation that's extreme ultraviolet and X-ray by molecules of oxygen and nitrogen. When these photons that are high energy receive absorption, they carry out increase of the energy that's kinetic of particles of gas. Because density of particles is low, the temperature that receives measurement by motion that's molecular can become very high, even though the air would produce feeling that's cold due to the number that's small of collisions. Temperature in this region can show variation that's significant depending on activity that's solar. The increase with height creates another structure of temperature that's stable when compared with the mesosphere that's cooler and positioned below. Energy that receives absorption here can also have effect on the expansion and contraction of the atmosphere that's upper. These changes have influence on the drag that receives experience by satellites. The exosphere is the layer that's atmospheric and outermost. It has its beginning above the thermosphere and gradually carries out merging with space. In this region, particles of gas receive spacing that's so wide that collisions are rare. Hydrogen and helium become more common relative to gases that are heavier. Some particles can carry out travel over distances that are long without carrying out interaction with others, following paths that are curved under gravity. A fraction that small of these particles may reach speeds that give them ability to carry out escape into space. The exosphere doesn't possess a boundary that's upper and sharply defined, as density undergoes decrease continuously. Despite its thinness that's extreme, it provides representation of the limit that's outer of the atmosphere's influence. This region carries out marking of the transition from envelope that's gaseous of Earth to the near vacuum of space. In the exosphere, particles of gas can carry out travel over distances that are long without carrying out collision. The spacing between particles is so large that interactions take place only occasionally. Motion receives influence more by gravity and radiation than by collisions that are frequent. Some particles carry out following of paths that are extended before changing direction. The behavior of gases here shows difference from that in layers that are denser and positioned below. Because collisions are rare, temperature and pressure receive definition differently than near the surface. The distribution of particles becomes more irregular with height. Elements that are lighter show dominance at these altitudes. The exosphere creates a transition that's gradual rather than a boundary that's sharp. The atmosphere receives composition mainly of nitrogen and oxygen. These two gases carry out accounting for nearly all of the volume of air that's dry. Their proportions stay fairly consistent in the atmosphere that's lower due to mixing. Other gases show presence in amounts that are much smaller. The mixture carries out behavior as a fluid, showing response to pressure, temperature, and motion. Interactions that are chemical between components take place under conditions that are suitable. The abundance that's relative of nitrogen and oxygen has influence on many properties that are physical. Their weights that are molecular have effect on profiles of density and pressure. This composition creates the structure that's basic of the air. Nitrogen carries out making up of about 78% of air that's dry. It exists primarily as a molecule that's diatomic, with two atoms of nitrogen that receive bonding together. Nitrogen is relatively stable and doesn't carry out reaction readily under conditions that are normal and atmospheric. Its abundance provides help in moderating activity that's chemical in the air. Cycles that are biological and chemical carry out movement of nitrogen between the atmosphere, land, and oceans. Despite its stability, nitrogen can carry out formation of compounds under conditions that are specific. These compounds assume roles in processes of soil and water. The proportion that's high of nitrogen contributes to the mass that's overall of the atmosphere. Its presence is consistent across most of the layers that are lower. Oxygen carries out accounting for about 21% of air that's dry. Like nitrogen, it receives finding mostly as a molecule that's diatomic. Oxygen carries out participation in many reactions that are chemical in the atmosphere and at the surface. It is essential for processes of combustion and respiration. The proportion of oxygen stays fairly uniform in the atmosphere that's lower. Some molecules of oxygen receive transformation into ozone in the stratosphere. Oxygen also carries out dissolving in water and carries out movement between the atmosphere and oceans. Its presence has effect on the density and behavior of air. Oxygen is a component that's key of the mixture that's atmospheric. Argon is the gas that's third most abundant in the atmosphere. It is a gas that's noble and is inert chemically under most conditions. Argon carries out making up of just under 1% of air that's dry. Because it doesn't carry out reaction readily, it undergoes accumulation over time. Its distribution is relatively uniform in the atmosphere that's lower. Argon doesn't assume a role that's major in processes of weather or climate. However, it contributes to the mass and pressure that are overall of the air. Its presence is useful in measurements that are scientific as a gas that's reference and stable. Argon stays mixed with other gases through motion that's atmospheric. Carbon dioxide shows presence in amounts that are much smaller. It creates a component that's minor of air that's dry, receiving measurement in fractions of a percent. Yet it assumes a role in the transfer of energy within the atmosphere. Molecules of carbon dioxide carry out absorption and emission of radiation that's infrared, which has influence on how heat carries out movement upward from the surface. Its concentration can show variation slightly by location and season, due to exchanges with oceans, soils, and organisms that are living. In the atmosphere that's lower, it stays mixed well because of movement of air that's continuous. Though showing presence in proportion that's small, its properties that are physical allow it to carry out participation in processes that are radiative and that have effect on structure of temperature. Carbon dioxide also carries out dissolving in water and carries out taking part in cycles that are chemical and natural. These exchanges take place steadily over time, without carrying out alteration of its role as a gas that's trace but active. Its weight that's molecular contributes modestly to the density of air. The behavior of carbon dioxide provides illustration of how even gases with concentration that's low can have influence on processes that are atmospheric. Gases that are trace include neon, helium, methane, and krypton. These substances show occurrence in concentrations that are very small when compared with nitrogen and oxygen. Each has properties that are distinct and chemical and physical that carry out determination of how it carries out behavior in the air. Neon and helium are gases that are noble and are largely unreactive. Methane is a hydrocarbon that's simple and that can carry out taking part in reactions that are chemical in the atmosphere. Krypton is another gas that's noble and inert, found in quantities that are minute. Although showing presence in amounts that are small, gases that are trace can carry out participation in transfer of energy and cycles that are chemical. Their distribution is generally uniform in the atmosphere that's lower because of mixing. Some gases that are trace have sources that are natural in oceans, soils, and processes that are geological. Others receive production through reactions that are chemical in the air itself. Together, they create a part that's small but measurable of composition that's atmospheric. Water vapor is a component that's variable of the atmosphere. Unlike nitrogen or oxygen, its concentration undergoes changes that are wide from place to place and from time to time. Air that's warm can carry out holding of more water vapor than air that's cool, leading to amounts that are higher in regions that are warmer. Water vapor carries out entering of the atmosphere mainly through evaporation from oceans, lakes and soil, as well as through transpiration from plants. It can also receive removal through condensation and precipitation. Because of these exchanges that are ongoing, its presence is uneven both vertically and horizontally. Water vapor has influence on density of air, pressure, and the transfer of heat. It carries out absorption and emission of radiation that's infrared, contributing to balance of energy. Its variability makes it a factor that's important in motion, that's atmospheric, and formation of clouds. Despite these effects, it stays only a fraction that's small of air, that's total by volume. The amount of water vapor shows dependence on temperature and location. In regions and seasons that are warmer, temperatures that are higher, allow more evaporation and content of moisture that's greater in the air. Over surfaces that are cooler or during periods that are colder, the capacity of air to carry out holding of water vapor receives reduction. Areas that are coastal and oceanic often have humidity that's higher than regions that are inland or arid. Altitude also has effect on water vapor, as conditions that are cooler at levels that are higher limit its concentration. Circulation that's atmospheric carries out transport of moisture from one region to another, carrying out shaping of its distribution. Conditions that are local, such as water on surface and vegetation, have further influence on the amount that's present. Because water vapor can undergo change quickly, measurements often show variation over timescales that are short. These variations have effect on patterns of formation of clouds and precipitation. The link between temperature and content of moisture is an aspect that's fundamental of behavior that's atmospheric. Water vapor assumes a role that's key in formation of clouds. When air that's moist undergoes rising and cooling, its capacity to carry out holding of water vapor undergoes decrease. Vapor that's excess then carries out condensation into droplets that are liquid and tiny, or crystals of ice. These particles carry out gathering around substances that are microscopic and known as nuclei of condensation. As more droplets or crystals carry out formation, clouds that are visible undergo development. The presence of water vapor therefore creates connection of evaporation from surface with processes that are atmospheric and aloft. Without moisture that's sufficient, formation of clouds would receive limitation. The distribution of water vapor provides help in carrying out determination of where clouds are most likely to show appearance. Its role extends beyond clouds to the release and absorption of heat during changes of phase. Through these processes, water vapor creates link of the movement of air with the transfer of energy. The weight of air above a given point creates air pressure. Molecules that make up air possess mass and experience pulling toward the surface by gravity. These molecules combined create a force that presses in all directions. Measurement of this force is expressed as pressure and shows decrease with height as the amount of air lying above becomes smaller. Pressure shows greater values near the surface where air density reaches higher levels. When pressure varies across regions, air movement results. Measurement of pressure delivers important information about conditions that are atmospheric. Units such as pascals or millibars receive common use. The concept of pressure creates links between gravity, mass, and motion in the atmosphere. Air pressure undergoes decrease with increasing altitude. As height builds, fewer molecules of air exist above a given level. This reduction in mass that lies above leads to pressure that's lower. The decrease happens rapidly near the surface and becomes more gradual at altitudes that are higher. Because pressure falls, air undergoes expansion as it rises. This expansion has effects on temperature and density. Instruments such as barometers carry out detection of changes in pressure with height. The relationship between altitude and pressure receives use in modeling that's atmospheric. Aircraft performance experiences influence from pressure that's lower at elevations that are higher. This pattern that's vertical is a property that's fundamental of the atmosphere. Air density also shows decrease with height. Density makes reference to the mass of air within a volume that's given. Near the surface, molecules exist closer together, producing density that's higher. With increasing altitude, the spacing between molecules undergoes growth. Density that's lower has effects on how heat receives transfer and how sound carries out travel. It also has influence on buoyancy and motion, that's vertical, of air parcels. Changes in density receive linking with changes in pressure and temperature. Many equations that are atmospheric carry out description of these relationships together. Observations provide confirmation that density shows decline. That's smooth with height. This pattern provides help in defining the structure of layers that are atmospheric. Air that's warmer is generally less dense than air that's cooler. When air receives heating, molecules move more rapidly and undergo spreading farther apart. This expansion brings down the mass per unit volume. Air that's less dense tends to undergo rising relative to air that's denser nearby. This behavior makes contribution to circulation that's vertical. Differences in temperature, therefore, have influence on pressure and wind. The relationship between temperature and density follows principles of behavior of gas. Content of moisture can also have effect on density, since water vapor is lighter than air that's dry. Variations in density carry out driving of many motions that are atmospheric. This property creates connection of heating with movement of air. Differences in air pressure carry out driving of movement of air that's horizontal. When pressure shows variation across a region, a force carries out action to move air from pressure that's higher to pressure that's lower. This movement provides help in balancing differences in pressure. The force that's responsible receives the name of pressure gradient force. Its strength shows dependence on how rapidly pressure undergoes change over distance. Other factors, such as rotation of Earth and friction, carry out modification of the motion. The flow that results creates patterns of wind of different scales. Differences in pressure arise from heating of the surface that's uneven. These gradients are central to circulation that's atmospheric. Movement of air that's horizontal carries out redistribution of energy and moisture. Movement of air that's horizontal receives the name wind. Wind provides representation of the flow of air across the surface of Earth and at various heights above it. This motion takes place because air shows response to differences in pressure from one place to another. Wind can receive measurement in terms of speed and direction, using instruments that receive design for observation that's atmospheric. Its movement provides help in distributing heat, moisture, and gases around the planet. Wind can take place on scales that are small and local or extend across regions that are large. Features of surface such as land, water, and terrain can have influence on its path. Friction near the ground carries out slowing of wind when compared with levels that are higher. Wind is therefore a mechanism that's key for transferring energy within the atmosphere. Wind carries out flow from areas of pressure that's higher to areas of pressure that's lower. This movement receives result from the force that's pressure gradient carrying out action on air. The greater the difference in pressure over a distance, the stronger this force becomes. Air starts to move to carry out reduction of the imbalance between regions. As wind undergoes development, other influences such as rotation of Earth and friction from surface carry out modification of its path. The flow that's direct from high to low pressure rarely stays straight. Instead, wind carries out adjustment until forces acting on it reach a balance. Systems of pressure are therefore linked closely with patterns of wind. These relationships create the basis for understanding circulation that's atmospheric. Rotation of Earth has influence on direction of wind. As the planet carries out rotation, air that's moving doesn't carry out travel in a line that's straight relative to the surface. Instead, its path shows appearance of deflection due to the frame of reference that's rotating. This influence shows increase with speed of wind and with distance from the equator. The effect undergoes change in direction between hemispheres that are northern and southern. It doesn't create motion by itself, but carries out alteration of the direction of air already set in motion by differences in pressure. This influence that's rotational provides help in shaping systems of circulation that are large-scale. Without it, patterns of wind would follow paths that are simpler. Its role is fundamental in providing explanation of directions of wind that receive observation across the globe. The effect that's Coriolis causes air that's moving to undergo curve over the surface of Earth. In the hemisphere that's northern, the deflection is toward the right of the direction of motion, while in the hemisphere that southern it is toward the left. The strength of this effect shows dependence on latitude and the speed of the air that's moving. It is weakest near the equator and strongest toward the poles. The effect that's Coriolis has influence on the formation of systems of wind that are large and currents of ocean. It provides help in maintaining the structure of cells of circulation and streams that are jet. This deflection that's apparent arises from rotation of Earth, rather than from a force that's direct acting on the air. Its influence becomes more noticeable over distances and time scales that are long. Patterns of wind that are large scale create cells of circulation that are global. These cells provide representation of patterns that are organized of air that's rising and sinking linked across latitudes. They undergo development because heating that's solar is uneven between the equator and the poles. Air that's warm undergoes rising in latitudes that are lower, carries out movement poleward at levels that are higher, cools, and then sinks. Air at surface then carries out return toward regions that are warmer, completing a loop of circulation. This structure provides help in redistributing heat across the planet. The arrangement of these cells receives influence from rotation and contrasts in temperature. They provide a framework for understanding belts of wind that are prevailing. Cells of circulation that are global create connection of processes of weather that are local with the movement that's overall of the atmosphere. The cells that are Hadley carry out operation between the equator and the subtropics. In these patterns of circulation, air undergoes rising near the region that's equatorial, where heating is strong. After rising, the air carries out movement poleward at altitudes that are higher. As it carries out travel, it cools and gradually sinks in the regions that are subtropical. Near the surface, air then carries out flow back toward the equator, completing the loop of circulation. This movement provides help in transporting heat away from latitudes that are low. The branch that's rising is often associated with development of cloud, while the branch that's sinking receives linking with air that's drier. The cells that are Hadley create a component that's major of circulation, that's atmospheric and global. Their position can undergo shift slightly with the seasons. These cells have influence on patterns of wind that are prevailing in areas that are tropical and subtropical. The cells that are feral exist positioned between the subtropics and mid-latitudes. These cells of circulation carry out operation in a zone between the cells that are Hadley and polar. Movement of air here is more complex and receives influence from interactions with cells that are neighboring. Near the surface, winds generally carry out movement poleward and eastward. Motions that are rising and sinking take place along boundaries between masses of air that are different. The cells that are feral provide help in transferring energy between latitudes that are lower and higher. Their structure is less symmetrical than the cells that are Hadley. Variations in temperature and pressure carry out guiding of their behavior. These cells make contribution to systems of wind that are prevailing found in regions that are mid-latitude. The cells that are polar carry out operation near the poles. In these cells, air that's cold and dense undergoes sinking over regions that are polar. This air then carries out movement toward latitudes that are lower near the surface. As it carries out travel, it can meet air that's warmer from mid-latitudes, leading to motion that's rising along boundaries. Air aloft then carries out return poleward, completing the loop of circulation. The cells that are polar are smaller in extent than the cells that are Hadley. Their strength can show variation with changes that are seasonal in heating that's solar. These cells provide help in moving air that's cold away from the poles. They create the component that's third of the model of circulation, that's 3-cell. Together with other cells, they carry out maintenance of balance that's atmospheric and large scale. Air that's rising near the equator makes contribution to formation of cloud that's frequent. Heating that's solar and strong warms air at surface, causing it to undergo expansion and ascent. As the air undergoes rising, it cools due to pressure that's lower at altitudes that are higher. Cooling can lead to condensation of vapor that's water. This process creates clouds in regions that are equatorial. The motion that's rising is part of the circulation that's broader within the cells that are Hadley. Movement that's upward and persistent provides support for development of cloud that's regular. Supply of moisture from surfaces that are warm provides enhancement of this effect. The combination of heat and moisture provides support for motion that's atmospheric and continuous. Air that's sinking in the subtropics receives linking with conditions that are drier. As air undergoes descent, it becomes compressed and undergoes warming. Warming carries out reduction of humidity that's relative, making formation of cloud less likely. This branch that's descending is part of the circulation of cell that's Hadley. The process leads to skies that are clearer in many regions that are subtropical. Air that's stable carries out limitation of mixing that's vertical and growth of cloud. Conditions at surface often provide reflection of the influence of this motion that's downward. Patterns of pressure in these areas are commonly associated with air that's sinking. This behavior provides illustration of how motion that's vertical has effect on distribution of moisture. The streams that are jet are bands that are narrow of winds that are strong in the troposphere, that's upper. These winds carry out flow at speeds that are high along paths that are relatively narrow when compared with air that's surrounding. They typically receive finding near the boundaries between masses of air that are large with temperatures that are different. Their position and strength can undergo change over time as patterns of temperature undergo shift. Streams that are jet generally carry out flow from west to east due to the influence that's combined of gradients of pressure and rotation of Earth. They assume a role in carrying out guiding of systems of weather across distances that are large. Aircraft often carry out use or avoidance of these winds, depending on direction of travel. The structure that's vertical and horizontal of streams that are jet provides reflection of the balance of forces carrying out action in the atmosphere that's upper. Their presence provides demonstration of how contrasts in temperature have influence on patterns of wind at altitudes that are high. Streams that are jet create formation near boundaries between masses of air of temperatures that are different. Differences in temperature that are strong over distances that are relatively short create gradients of pressure that are steep at levels that are high. These gradients bring about currents of air that are fast-moving and concentrated in zones that are narrow. The contrast between air that's warm and cold provides help in maintaining the strength of these winds. Shifts that are seasonal in distribution of temperature can carry out alteration of the position of these boundaries. As a result, streams that are jet can carry out movement north or south during the year. Their speed and path receive influence from patterns of circulation that are large-scale. Waves and disturbances can undergo development along them, affecting motion that's downstream. This relationship between contrast of temperature and speed of wind is a feature that's key of circulation that's upper level. Temperature of air receives influence from radiation that's solar. Energy from the sun reaches the atmosphere in the form of waves that are electromagnetic. Some of this energy receives absorption by gases and particles, carrying out warming of the air. The amount of heating shows dependence on factors such as angle of sunlight and composition that's atmospheric. Surfaces on Earth carry out absorption of radiation and carry out transfer of heat to the air positioned above. Differences in heating across regions create variations in temperature. These variations make contribution to differences in pressure and movement of air. Clouds and particles can also carry out reflection or absorption of radiation, carrying out modification of patterns of temperature. The balance between energy that's incoming and outgoing carries out shaping of structure of temperature that's atmospheric. The atmosphere carries out absorption and re-emission of some of heat that's outgoing from Earth. after the surface undergoes warming, it carries out emission of energy in the form of radiation that's infrared. Gases that are certain in the atmosphere carry out absorption of part of this radiation, and then carry out emission of it in directions that are various. This exchange carries out slowing of the rate at which heat carries out escape directly to space. The process has effect on temperature at heights that are different in the atmosphere. It involves gases such as vapor, that's water, and dioxide, that's carbon. The absorption and emission take place continuously as energy carries out movement through the system. This interaction between radiation and gases has influence on patterns of temperature that are vertical. It creates part of the balance of energy that's overall of the planet. This process makes contribution to the regulation of temperatures at surface. By carrying out absorption and re-emission of radiation that's infrared, the atmosphere carries out moderation of the transfer of heat from the surface to space. Without this effect, temperatures at surface that are average would show difference from values that are present. The process doesn't carry out operation uniformly, but shows variation with concentrations of gas and cover of cloud. It carries out work alongside reflection of sunlight and storage of heat in oceans and land. These influences that are combined provide help in maintaining a range of temperatures that are suitable for many processes that are natural. Variations in this balance can lead to changes in distribution of temperature. The atmosphere therefore carries out action as a medium through which energy receives redistribution. The atmosphere provides allowance for light that's visible from the sun to reach the surface of Earth. Most radiation that's solar and incoming in the range that's visible carries out passage through the air with absorption that's limited. This transmission provides enablement for heating of surface, which then has influence on temperature of air above. Some wavelengths receive scattering or absorption, but a portion that's large continues downward. The clarity of the atmosphere has effect on how much light reaches the ground. Particles, gases, and clouds can carry out modification of this passage. The balance between transmission and absorption carries out shaping of the distribution of energy. This interaction creates part of the link between input that's solar and motion that's atmospheric. Some radiation that's solar and incoming receives reflection by clouds and particles. Reflection takes place when radiation carries out encounter of surfaces or particles that carry out redirection of energy back towards space. Clouds, particles that are airborne, and the surface itself all make contribution to this process. The proportion that receives reflection shows dependence on cover of cloud, concentration of particles, and characteristics of surface. Reflection carries out reduction of the amount of energy that receives absorption by the surface and atmosphere that's lower. This provides help in influencing patterns of temperature. The balance between radiation that's reflected and absorbed is part of the system of energy of Earth. Variations in reflection take place across regions and seasons. This process carries out operation continuously as sunlight carries out entering of the atmosphere. Scattering of sunlight by molecules of air provides the sky with its color. When sunlight carries out passage through the atmosphere, it carries out interaction with molecules of gas and particles that are small. Wavelengths that are shorter of light receive scattering more efficiently than wavelengths that are longer. This scattering carries out distribution of light in directions that are different. The process is most noticeable when the sun is positioned above the horizon. The effect shows dependence on the size of particles relative to the wavelength of light. Changes in concentration of particles can carry out alteration of the appearance of the sky. Scattering is a property that's optical and fundamental of the atmosphere. It provides demonstration of how light carries out interaction with matter. Wavelengths that are shorter of light carry out scattering more strongly than wavelengths that are longer. This behavior receives result from interactions between light and particles much smaller than the wavelength. Light that's blue and violet receive scattering more than light that's red. The difference in efficiency of scattering provides explanation of variations in the appearance of the sky. The same principle has influence on the color of sunlight when it carries out passage through paths that are longer in the atmosphere. The process shows dependence on size and concentration of particles. Scattering doesn't carry out changing significantly of the energy that's total, but carries out alteration of its direction. This property receives description by laws that are physical and well established. It is one example of how radiation carries out behavior in gases. Clouds create formation when air becomes saturated with vapor that's water. Saturation takes place when the amount of vapor that's water equals the maximum that air can carry out holding at a temperature that's given. When saturation receives reaching, vapor that's excess undergoes change of phase into droplets that are liquid or crystals of ice. This change has requirement of the presence of particles that are small, that carry out action as surfaces for condensation. Air that's rising and that cools often reaches saturation. The process creates links of temperature, pressure, and content of moisture. Formation of clouds therefore shows dependence on both conditions that are thermodynamic and physical. Once they create formation, clouds can have influence on radiation and precipitation. They provide representation of collections that are visible of water that's condensed in the atmosphere. Saturation takes place When air can't carry out holding of vapor, that's water additional at a temperature that's given. The capacity of air to carry out containing of vapor, that's water, shows increase as temperature undergoes rise, and shows decrease as temperature undergoes fall. When the amount that's maximum receives reaching, the air receives description as saturated. Any cooling that's further or addition of moisture leads to condensation. This state receives definition by the balance between evaporation and condensation. Humidity that's relative carries out expression of how close the air is to saturation. At saturation that's full, humidity that's relative is 100%. This condition often comes before formation of cloud. The concept creates link of temperature with content of moisture. Air that's cooling can lead to condensation. As temperature of air undergoes decrease, its ability to carry out retention of vapor, that's water, receives reduction. Vapor that's excess then undergoes change into droplets that are liquid or crystals of ice. This change of phase carries out release of energy in the form of heat that's latent. Cooling can take place when air undergoes rising, carries out movement over a surface that's cooler, or carries out mixing with air that's colder. The rate of condensation shows dependence on content of moisture and the presence of nuclei of condensation. The process creates the basis of development of cloud. Condensation also makes contribution to fog and dew under conditions that are suitable. It is a part that's key of the cycle of water that's atmospheric. Condensation brings about droplets that are water and tiny or crystals of ice. These particles are typically very small and can stay suspended in the air. Their formation has requirement of surfaces such as particles of dust or salt. The number and size of droplets have influence on properties of cloud. Temperature carries out determination of whether droplets that are liquid or crystals of ice are more common. The presence of these particles has effect on how clouds carry out interaction with radiation. Droplets can carry out combination or growth under conditions that are certain. The formation of these particles that are small is essential for precipitation to undergo development. This step creates connection of moisture in the air with structure of cloud that's visible. These droplets or crystals carry out clustering to create clouds. As condensation keeps going, numbers that are large of particles carry out gathering in a region of air that's saturated. Their presence, that's collective, makes the cloud visible. Motion of air that's upward can carry out keeping of these particles suspended. The thickness and extent of a cloud show dependence on supply of moisture and motion that's atmospheric. Forms of cloud that are different arise from variations in height and stability. The arrangement of droplets and crystals has influence on how clouds carry out reflection and absorption of radiation. Formation of cloud therefore creates link of processes that are microscopic with patterns that are atmospheric and large scale. The process of clustering is ongoing as air carries out movement and cooling. Types of cloud show variation according to height and appearance. Classification often carries out grouping of clouds into levels that are high, middle, and low based on altitude. Their shapes and structures also show difference, providing reflection of processes of formation. Some show appearance as sheets that are layered, while others show development that's vertical. Conditions of temperature and moisture at heights that are different have influence on their form. Observations of type of cloud provide help in describing conditions that are atmospheric. Each category receives association with composition of particle and motion that are typical. The distribution of types of cloud undergoes change with patterns of circulation. This variety provides illustration of how structure that's atmospheric has effect on features that are visible. Clouds that are high level often contain crystals of ice. These clouds create formation at altitudes where temperatures are low enough for water to undergo freezing. Crystals of ice can take shapes that are various depending on temperature and humidity. Their structure has influence on how light carries out passage through them. Clouds that are high level typically receive finding above 6 kilometers. They often show appearance that's thin because of the moisture that's limited at those heights. Motion of air at these levels can carry out spreading of them over areas that are wide. Their presence provides indication of conditions in the troposphere that's upper. These clouds carry out interaction with radiation differently from clouds that are lower. Clouds that are mid-level can contain both droplets that are water and ice. These clouds create formation at altitudes that are intermediate, where temperatures show variation around the point that's freezing. The mixture of particles that are liquid and solid has effect on their appearance and behavior. Their development shows dependence on air that's rising and availability of moisture. Clouds that are mid-level often show appearance as layers or patches. They can undergo thickening when moisture that's additional receives supply. The balance between droplets and crystals of ice has influence on processes of precipitation. These clouds provide information about structure of temperature in the troposphere that's middle. Their properties undergo change with conditions that are atmospheric. Clouds that are low level are mostly composed of droplets that are water. They create formation where temperatures of air are generally above freezing. Air that's moist near the surface can undergo condensation into clouds under conditions that are suitable. These clouds often show appearance as sheets or layers that are broken. Their base is typically below 2 kilometers. Clouds that are low level can carry out covering of regions that are large. They assume a role in carrying out reflection of sunlight and affecting temperatures at surface. Their formation receives influence from heating and cooling at surface. These clouds are a feature that's common of the atmosphere that's lower. Precipitation creates formation when particles of cloud become large enough to undergo fall. Droplets and crystals that are small can carry out combination through collision and coalescence. Crystals of ice may undergo growth by carrying out collection of vapor that's water directly. As particles show increase in size, gravity carries out overcoming of motion of air that's upward. The particles that are falling may stay liquid or frozen depending on temperature. Precipitation includes rain, snow, sleet and hail. The process creates link of microphysics of cloud with water at surface. Not all clouds carry out production of precipitation. Conditions such as content of moisture and motion that's vertical carry out determination of its development. The cycle that's water involves evaporation, condensation, and precipitation. Water carries out movement continuously between the surface and the atmosphere. Energy that's solar carries out driving of evaporation from oceans, lakes, and soil. Vapor, that's water, undergoes rising, cooling, and condensation into clouds. Precipitation carries out return of water to the surface. Some water carries out flow into rivers, or carries out seeping into the ground. Plants make contribution of moisture through transpiration. This cycle carries out redistribution of water across regions. It carries out operation on timescales from hours to years. Evaporation carries out transfer of water from the surface into the atmosphere. Water that's liquid gains energy and undergoes change into vapor that's water. This process takes place over oceans, lakes, rivers, and soil that's moist. Temperatures that are higher carry out increase of the rate of evaporation. Wind can also provide enhancement of the transfer by carrying out removal of air that's moist from the surface. Evaporation carries out absorption of heat, which has influence on temperature that's local. The vapor that's water and added becomes part of moisture that's atmospheric. This step is a link that's major in the cycle that's water. It creates connection of water at surface with formation of cloud. Transpiration from plants also carries out addition of vapor that's water to the air. Plants carry out release of moisture through openings that are small in their leaves. This process takes place during the exchange of gases that receive need for growth. The effect that's combined of evaporation and transpiration often receives description together. Moisture that receives release by plants makes contribution to humidity in the atmosphere that's lower. The rate shows dependence on type of plant, moisture of soil, and temperature. Transpiration creates link of activity that's biological with processes that are atmospheric. It assumes a role in balance of moisture that's regional. This transfer is continuous in areas that are vegetated. Vapor that's water and condensed can carry out return to the surface as rain or snow. When particles of cloud undergo growth and fall, they carry out transport of water back to the ground. The form of precipitation shows dependence on conditions of temperature along the path that's downward. Droplets that are liquid bring about rain when air is warm. Crystals of ice or flakes reach the surface as snow when temperatures stay low. Some precipitation may undergo change of form before reaching the ground. This flow that's return carries out completion of part of the cycle that's water. It carries out replenishment of supplies of water at surface and ground. The process carries out redistribution of moisture across regions. Circulation that's atmospheric carries out redistribution of heat around the planet. Movement of air carries out carrying of energy from regions that are warmer toward ones that are cooler. Motions that are rising and sinking make contribution to transfer of heat that's vertical. Winds that are horizontal carry out spreading of energy across latitudes. Oceans and surfaces of land have influence on how this redistribution takes place. The process carries out reduction of contrasts in temperature between regions. Patterns of circulation show variation with season and location. This movement of heat is essential for maintaining balance of energy. It creates link of conditions that are local with behavior that's atmospheric and global. Oceans and surfaces of land have influence on movement of air. Water and land carry out heating and cooling at rates that are different. These differences create variations in pressure that carry out driving of winds. Coastlines often undergo experience of flows of air shaped by these contrasts. Mountains and terrain also carry out modification of patterns of wind. Characteristics of surface have effect on how energy receives absorption and release. Vegetation and moisture of soil have further influence on conditions of air that are local. These interactions create connection of the atmosphere with the surface. The result is a pattern that's complex of motion, shaped by features that are underlying. Air undergoes expansion and rising when surface heating takes place. When the ground carries out absorption of energy that's solar, it carries out warming of the air positioned directly above it. The air that's warmed becomes less dense than air that's surrounding and cooler. This difference leads to motion that's upward. Air that's rising can carry out transport of heat and moisture to levels that are higher. The strength of this process shows dependence on contrast in temperature. It makes contribution to circulation that's vertical in the atmosphere that's lower. The motion creates link of conditions at surface with development of cloud. Air that's rising undergoes cooling as pressure shows decrease with height. Pressure that's lower at altitudes that are higher provides allowance for parcels of air to undergo expansion. Expansion has requirement of energy, which brings about cooling as a result. This cooling takes place even without exchange of heat with air that's surrounding. The rate of cooling shows dependence on content of moisture. As temperature undergoes fall, humidity that's relative shows increase. Cooling of air that's rising often leads to condensation. This process is central to formation of cloud. It creates connection of motion that's vertical with change in temperature. Air that's cooling can lead to formation of cloud. As temperature of air undergoes drop, its capacity to carry out holding of vapor, that's water, shows decline. When saturation receives reaching, condensation starts to begin. Droplets or crystals of ice create formation around particles that are small. Cooling that continues can carry out increase of thickness of cloud. Motion that's upward provides support for the growth of layers of cloud. The process shows dependence on both moisture and stability that's atmospheric. This mechanism creates link of thermodynamics with structures of cloud that are visible. Air that's descending undergoes warming as it receives compression. As air carries out movement downward, pressure that's surrounding shows increase. The compression carries out raising of the temperature of air. Air that's warmer can carry out holding of more vapor that's water, carrying out reduction of humidity that's relative. This warming tends to carry out inhibition of formation of cloud. Motion that's descending is often associated with conditions that are clearer. The process has influence on patterns that are regional of moisture. It provides representation of the branch that's downward of circulation that's atmospheric. Air that's stable shows resistance to motion that's vertical. In conditions that are stable, air that's displaced tends to carry out return to its level that's original. This takes place when the structure of temperature that's surrounding carries out limitation of movement that's buoyant. Layers that are stable can create formation. When temperature shows decrease, that's slow with height or shows increase. Such conditions carry out reduction of mixing between levels. Clouds in air that's stable often show appearance as layers rather than towers that are vertical. Stability has effect on how pollutants and moisture receive distribution. It is a factor that's important in structure that's atmospheric. Air that's unstable provides encouragement for movement that's vertical. When parcels of air keep rising after receiving lifting, the atmosphere receives consideration as unstable. This situation takes place when temperature shows decrease that's rapid with height. Motion that's rising can carry out transport of heat and moisture upward. Currents that are vertical become stronger under conditions that are unstable. Development of cloud often receives enhancement in such environments. Mixing between levels shows increase. Instability creates link of gradients of temperature with motion of air. Stability that's atmospheric has effect on development of cloud. Air that's stable provides support for forms of cloud that are layered with growth that's vertical and limited. Air that's unstable shows favor for clouds with extent that's vertical and greater. The degree of stability has influence on how parcels of air carry out movement after receiving displacement. Profiles of temperature and moisture carry out determination of this behavior. Stability also has effect on processes of precipitation. Observations of type of cloud can provide indication of conditions of stability. This relationship creates connection of structure that's thermal, with features that are atmospheric and visible. Inversions of temperature take place when temperature of air shows increase with height. This pattern is opposite to the decrease that's usual in the troposphere. Inversions can create formation near the surface or at levels that are higher. They create conditions that are very stable and that carry out limitation of mixing that's vertical. Air that's cooler becomes trapped beneath air that's warmer. This structure has effect on formation of cloud and fog. Inversions can carry out persistence under patterns of weather that are certain. They provide representation of an arrangement of temperature that's vertical and distinct. Inversions can carry out limitation of mixing of air that's vertical. When air that's warm exists positioned above air that's cooler, motion that's upward receives suppression. Pollutants and moisture may stay confined below the inversion. Turbulence receives reduction in such conditions. Layers of cloud may create formation at the level of inversion. Conditions at surface can show difference from those aloft. The persistence of inversions has influence on behavior that's atmospheric and local. This effect provides illustration of how structure of temperature carries out control of motion. The atmosphere provides protection for Earth from many meteoroids that are small. As objects that are small carry out entering of the atmosphere, they carry out collision with molecules of air. Heating that's frictional causes most of them to carry out burning up before reaching the surface. This process takes place mainly in the mesosphere. The interaction carries out conversion of energy that's kinetic into heat and light. Only fragments that are larger may carry out survival to levels that are lower. The atmosphere, therefore, carries out action as a layer that's protective. This function is part of its role that's broader in providing support for processes that are natural. Friction with air causes most meteoroids that are small to carry out burning up. Speeds that are high during entry bring about heating that's intense. The surface of the object undergoes ablation as material receives removal. Energy receives transfer to air that's surrounding. The object often carries out disintegration before reaching the ground. This process carries out reduction of the number of impacts at the surface. It shows dependence on speed of entry, angle, and size. The interaction provides demonstration of the effect of density that's atmospheric at altitude that's high. The ionosphere is a region of particles that are charged within the atmosphere that's upper. It carries out overlapping of parts of the thermosphere. Radiation that's solar carries out removal of electrons from molecules of gas, creating ions. This region contains layers with concentrations that are varying of particles that are charged. Its properties undergo change with activity that's solar and time of day. The ionosphere has effect on how certain types of radiation carry out movement through the atmosphere. It provides representation of an area where processes that are electrical are significant. Radiation that's solar can carry out ionization of gases that are atmospheric. Radiation that's ultraviolet and X-ray and high energy provides energy that's enough to carry out removal of electrons from atoms and molecules. This process creates ions that are positively charged and electrons that are free. Ionization takes place mainly at altitudes that are high where radiation is strongest. The concentration of ions shows variation with conditions that are solar. Recombination can also take place when electrons carry out rejoining of ions. These processes have influence on the state that's electrical of the atmosphere that's upper. The ionosphere has influence on the transmission of waves that are radio. Particles that are charged can carry out reflection or refraction of frequencies that are radio and certain. This provides allowance for signals to carry out travel beyond the horizon. The effect shows dependence on frequency and conditions that are ionospheric. Variations take place between day and night. Activity that's solar can carry out modification of paths of signal. The interaction between waves that are radio and particles that are charged is studied well. It provides demonstration of the impact that's practical of processes that are upper atmospheric. The atmosphere carries out exertion of pressure on all surfaces at the surface of Earth. This pressure result from the weight of air that's overlying. It carries out action in all directions. Organisms that are living and structures are adapted to this force that's constant. Pressure can show variation with systems of weather and altitude. Instruments carry out measurement of these changes for observation. The value shows decrease with elevation. This pressure is a property that's fundamental of the atmosphere. Pressure that's atmospheric is commonly measured with a barometer. Barometers carry out detection of changes in the force that receives exertion by the air. Designs that are different carry out use of liquids or sensors that are mechanical. Measurements receive expression in units that are standard. Readings of pressure provide help in identifying systems of weather. Observations over time provide revelation of patterns of change. These measurements provide support for study that's atmospheric. The instrument creates link of force that's physical with data that's recorded. Systems of pressure undergo shift over time due to movement of air. Regions of pressure that's higher and lower carry out development and movement. These shifts receive driving from differences in temperature and patterns of circulation. As systems carry out movement, patterns of wind undergo change. The movement can take place over days or periods that are longer. Interaction between systems carries out shaping of conditions that are regional. Tracking of changes in pressure provides help in describing behavior that's atmospheric. This motion provides reflection of the nature that's dynamic of the atmosphere. Changes that are seasonal have influence on patterns of circulation that are large-scale. Variations in heating that's solar across the year carry out alteration of contrasts in temperature. These changes carry out shifting of belts of wind and cells of circulation. The position of streams that are jet can also show variation. Patterns of air that's rising and sinking carry out adjustment with the seasons. Oceans and land carry out response differently to heating that's seasonal. These adjustments have effect on motion that's atmospheric globally. Variation that's seasonal is a feature that's regular of circulation. The atmosphere carries out interaction continuously with oceans, land and ice. Exchanges of heat, moisture and gases take place at boundaries. Features of surface have influence on temperature of air and movement. In turn, the atmosphere has effect on conditions at surface. These interactions create a system that's connected. Energy and matter carry out movement between components. The coupling carries out operation on many timescales. This relationship creates link of processes that are atmospheric with the system of Earth that's broader. The composition and structure of the atmosphere provide support for many processes that are natural on Earth. The mixture of gases provides enablement for transfer of energy and cycles that are chemical. Layering and circulation carry out distribution of heat and moisture. Patterns of pressure and temperature provide allowance for clouds and precipitation to create formation. Interactions with the surface create connection of the atmosphere to oceans and land. Properties that are protective and radiative have influence on conditions at the surface. These features that are combined carry out definition of the atmosphere as a component that's active of the planet.